So, first of all, good morning to all of you, and we are really very proud to receive all of you here today, because this is where we start life again. Yesterday we tried to remember what was the past. Now we are in phase. And all the objectives of the Academy is just not only to give awards. This is very important. There's the recognition of the quality and the merits of our fellows, but also to recognize where we can be and where we want to be in the future. What is our roadmap? We discussed somehow yesterday these objectives, and this, of course, depends in the strategy of the divisions, because we need together to walk together this pathway that we want to do for the future. And we identify several challenges, not only in advising nationally our political policymakers that are responsible for the challenges that we have in science, locally, regional, which from each state is not only in Europe, but globally. We have to make this type of attempts, but see how we can really work together to reach further goals. On globalization, this is something which is a landmark for our academy, is that we want to work together, so we can see how we can make bridges with the different continents, and how we can have a strategy for making science more and more global. And of course, it is very important that even for the new fellows and for all the members of our academy to understand what are the challenges, what are the pathways that the visions, what is the vision of the divisions, and we can discuss and try to see how we can work together and try to follow with independency, as it was said yesterday, that science requires, our pathway, and see how we can together even give ideas and to see what could be the key points in the remarkable points of our strategy that could serve as a whole our academy. So this morning we will spend this type of discussion, so I will ask you for interventions, not only just to listen, but to be active in asking questions and trying to see how this will be moved further. This is in fact the great opportunity for all of us to interfere in the policy and what we want the academy to be, and how we can really support and try to see what type of events that we should organize, how the divisions could interpenetrate between them, as we discussed yesterday. And therefore, this is the moment to do so. So this is in the name of the executive of Hélène, which is our perpetual secretary, and the vice president, Alain. I declare open the sections of today, and I invited our colleague, José Carrillo, the head of division of mathematics, to explain what he thinks we should be going. So let's.
It's okay. Okay, so I made a presentation with a basic introduction of what the section is about, just for general also information. But let me just introduce myself. I'm the head of the division I'm at the University of Oxford, and no, it doesn't work. Yeah, good, great. And the officers of the division, you have them here, which they have been very helpful and quite active during the years I've been as head of the division. It's my end of the second year and a half, so next year is my third year. So the officers are listed here, Jean-François Legal from Paris-Orsay, Donatella Marini from Universitat de Pavia, Luis Vega from Universidad del País Vasco, and Tom Yang from City University of Hong Kong. Let me just mention before entering into the matter related to the academy, the basic areas of research of the members of the division, just very briefly, applied math, pure math, and statistics. But I like always to introduce the definition of mathematics and statistics given by the Oxford Dictionary. Okay, so I mean, as you all know, and I don't have probably to say that much, mathematics is about the abstract science of numbers, quantities, and spaces, and abstract concepts, and as I said, that's the pure side, or the applied side to other disciplines, like physics, engineering, and so on. And also it's important to define statistics, which, as defined as the Oxford Dictionary, is the practice of science of collecting and analyzing numerical data in large quantities, especially for inferring representative information. Okay, so to be more specific, in applied math, most of our, let's say, members, they can be included in some of these areas that are listed there that I'm not going to read. But let me just mention that in applied math, contrary to the typical view that people have about mathematics, what you want to do is to explain some phenomena that may occur in the real world. And for instance, just to give examples, how a leopard gets its spots, how cells crawl to chemical cues, due to chemical cues, to explore quantum theory or relativity, study the math of stock markets, many, many other applied directions. And let me mention here a few of them that constitute the realm of applied math. Partial differential equations, numerical analysis, stochastic analysis. I would say modeling, simulation, control, and optimization, which has a very important role in possible applications and in the connection, especially with policymakers and industry. So, yeah, well, what is it about applied math? So here I have an example, which is just mine, and if probably he could run the video. So what you are trying to do in applied math is to try to explain the phenomena that you have in the first row, which are experiments, based on some mathematical model. So that is what is called the mathematical modeling cycle, in which you start with some basic ideas for how to represent what is going on in the phenomena, which is improved by talking to the experimentalist, trying to do parameter estimation, and trying to use data in order to infer parameters that represent the reality. So you please run it again, because and now let me explain you what you had there. You had just a colony of cells that are growing. It's tissue growth on in vitro. And in some of the experiments there, in these 4 experiments that are shown there, the cells have been genetically treated in such a way that certain proteins of certain pathways have been knocked down in such a way that the cohesive forces between the cells are changing. And this is just an example of this numerical solution of a system of partial differential equations that have been obtained to represent that phenomena in a kind of starting from microscopic modeling of this cell behavior. So, I mean, just as an example of math modeling cycle in which this is where all these tools that are listed in the left-hand side for you are important in order to develop the theory. Pure math, as you know, and probably you have heard that many times before, some years ago there was always a discussion about what is pure math versus applied math. Pure math is about proving things that are not primarily motivated by applications, like, they can come from applications, but the pure mathematicians, they are not motivated directly by the applications, but just because of the intellectual challenge and the beauty of working on the logical consequences of these basic principles. But, well, I mean, some examples of pure math. Let me just show you here the periodic tiling that we have at the entrance of the Oxford Mathematical Institute that was created by, or introduced by Roger Penrose, that got the Nobel Prize in Physics for his contributions in relativity. So you see that people that work in pure math, they can have also a big impact in other areas just because of their interest in just concepts that not necessarily have a direct application. Well, I mean, I just show another more kind of periodic tiling on the side. As you see, I mean, mathematics is devoted to understand this, the difference between these things. These concepts, for instance, which may have a certain beauty behind, obviously, but also certain importance then later on. And I'm just listing a list of the basic areas that also members of the division do, and they form certainly the core of pure mathematics. Okay, finally, statistics. So statistics is about the treatment of large data, and we know that now this has become the central core of many parts of science, how to deal with the large amount of data that we have, especially emerging from science and industry. And statistics develops mathematical methods to understand the value of this data to society. So some of the lines of research of researchers of the division, again, that we would like to involve, are listed here. Okay, just some comment about these kind of divisions. Divisions are always bad, no, in a sense. And we know that from the own history of mathematics. If you have heard about Hardy's Apology of a Mathematician, I mean, years ago, Hardy, which is a very well-known British mathematician, he defined pure mathematics as being the beautiful part of mathematics against the dull part of mathematics that was applied mathematics. That was many years ago. We're talking about 70 years ago. Of course, modern views are totally different. And I would say that mathematicians all over the world now recognize more and more the great value of being agnostic about this division between pure and applied, and against all these historical views from the past. And in fact, mathematics has its strength as a whole, being able to use very deep mathematical concepts with unexpected applications. And some examples nowadays used is topological data analysis, for instance. It was just born from very deep concepts in topology, and is used nowadays a lot in the treatment of large amount of data, which is a completely independent tool from statistical analysis or statistical tools. Other examples, approximation theory in data compression. We heard from one of our Blaise Pascal medal yesterday. All these good tools for compression of data, images, and so on. I would like to mention about digital virtual twins in industry. This is very much in the direction of industrial mathematics. It's one of the main things right now in modeling, simulation, and optimization, create like virtual twin of certain process that then you can kind of model or simulate in silico and not to save time and cost. And another one that came to my mind is, for instance, the use of optimal transport tools in data science. Optimal transport is also a kind of very theoretical side of calculus of variations in mathematics that nowadays is being used for analysis of large dimensional data. So the point I want to make is this. Mathematics is really everywhere and is becoming more and more present in our society. And we had to transmit as an academy this message, and also to policymakers. Finally, I want to mention, let's say, the source of most of the exceptional researchers that we have in our membership. Of course, it comes from people that are very active, outstanding researchers belonging to mainly learned societies in Europe or related to national learned societies. I'm listing the European learned societies in the field. The European Math Society, the Federation of National Statistics European Societies, the European Consortium for Math in Industry, the European Society for Mathematics and Theoretical Biology, and the European Service Network of Mathematics for Industry and Innovation. Future. So future about this in mathematics is always complicated to say something. I'm not going to try to do things like Hilbert did in the first International Congress of Mathematicians, but just to say a few things that I believe that are important, and they are things that we are going to see in the next years, is of course in pure mathematics is much harder, but I would say that what we have learned in the last 20 years in pure math is that the cross-pollination between areas gives rise usually to important developments in pure mathematics. So I think still interaction between differential geometry and calculus of variations, stochastic analysis and discrete math, algebraic structures and discrete math, just to name a few. I'm sure they will give rise to very important advancements in the pure math direction. But I would say that we will see also a widespread use of modeling using differential equations in industry and in life sciences and in social sciences. It has been the case in physics and chemistry for many years, but I think now in life sciences and in social sciences it will be the next step. The mathematical foundations of data science, I think this is something that already is going on and very important across not only Europe but worldwide. And we will see, in general, a sustained growth of the application of mathematical tools in the sciences, I would say. And concerning the future of the division of the academy, I think one important point is to increase the diversity of the members of our division in many aspects. I'm listing some of them here, but I'm not restricted to that. But I would even add one related to the discussion that we had yesterday, but just to mention some, the field of mathematical research, European countries of origin, countries of affiliation, and the obvious ones of gender, and I would add one more, of age. Because I think the point that somebody made yesterday about including some younger people in the academy, I think it would be important. Our division, in particular, has still the potential to expand more to achieve, with the objective of achieving a better representation of mathematics done by Europeans worldwide. I think still there is a better job that we can do in several areas. And right now we have 125 members, I just checked yesterday. I think the objective that would be that in this way, by expanding and achieving a better representation, we will increase somehow the standing of the academy and the division as a trustworthy consultation body for research in mathematical sciences by the highest research institution in Europe, and we count with the members of the academy and our president to pass this message to the corresponding policy makers. And I'm all yours for questions.
So there's 125 members in mathematics division.
Yes.
What roughly is the representation numbers between pure mathematics, applied and statistics? Just to get an idea of whether it's quite even or whether it's largely one or the other.
That's a very good question. I didn't do this job. I didn't try to classify all people because sometimes it's very difficult to classify them.
Yes,
I don't consider myself an applied mathematician or a pure mathematician. I would consider myself both. So that's the first answer I have to that question. But it's true that I would say it's a bit, probably there is less representation overall of statistics, certainly, right now. And pure math versus applied math is a bit uneven, yes, but not that
Which way?
in the direction of applied math, I would say. But I mean, these things is how developed the things have developed historically by the nominations of the previous heads of division, and it's not something that it can be adjusted fast. But,
No.
you know, we have been doing a healthy number of nominations per year since I started 2.5 years ago, of the order of 6 to 8, and this needs some time.
What about the number of women and men is in your division? Is that?
Again, I cannot tell you the numbers, but certainly mathematics in general is a science in which the number of women in the past was not high, and this is something that we are very aware of, and we have started to take some decisions on it. Lately, in all the nominations, we have had a good number of women in the nominations in the last 3 years too. So these things are naturally changing also because the composition of researchers in mathematics is also the number of female researchers is increasing.
Yeah, for instance, at your institute, the number of women is definitely more than it used to be.
Yes, in mathematics especially, we see that, especially in the younger generation. So, I mean, my generation already.
Yeah.
I would like to ask you, what do you think will be the influence of deep learning and artificial intelligence in the progression of mathematics and the new theorems, proofs of new theorem? How do you think this could be implemented?
Yeah, I think this is a very good question. That's why I put the mathematical foundations of data science. I think mathematics has a role there, and it has to go hand in hand with computer scientists in the sense of trying to underpin some of the algorithms that are already being used, or trying to come out with different ideas to do that. And in fact, there is a clear direction now in many top departments in mathematics in the world to go in these kind of research topics. So it's already going on. I mean, artificial intelligence, I would include machine learning or in the same, or you know, global optimization in large dimensions. All of these. It looks less fancy when we say that than when we say artificial intelligence, but we are talking about the same thing. If we talk about optimization in large dimensions, I mean, this can be applied directly to artificial intelligence. So there is, I think there is certainly quite big room for mathematics in there. Yeah.
In applied mathematics, how do you see the relative role of increased number crunching power versus better algorithms? I mean, just technically, computers perform always better and better in just calculation, but algorithms apparently seem to evolve even faster and better in performance.
Well, I mean, that's is a very good question. We were having a discussion yesterday with one new member of the academy, Jin Chao, that is sitting over there. You know, for instance, just to give an example that may some people here may know, it's about the fast Fourier transform. The fast Fourier transform is a way of computing a kind of a double sum of numbers in a very fast way. It sounds very non-appealing, but it's behind any signal processing algorithm that you have. Use it in your cell phone every day. So computing blindly a double sum of numbers in that way is what is called a convolution. It takes n square cost, while with a fast Fourier transform it takes n log n. And it looks nothing, but it makes the difference of running it in 2 seconds or running it in milliseconds. So what I mean is that the importance of the complexity of algorithms is huge. Reducing from n to the 3, an algorithm to n squared is a big step. And that makes the difference of running it in a cluster of computers or running in a laptop. So of course it's important. And that's the way in which the numerical analysis, say, goes in the improvement of the cost, computational cost in general.
Okay, thank you. I apologize. I was unable to attend yesterday.
So
Thank you.
I think on time, now it's time to give the floor to Paul, to the physics division.
Okay, it seems to work. Okay. Okay, now for the physics division, so we have in this division we have a bit more than 100 fellows, which is far, in spite of the fact that we have a few Nobel Prizes in our division, it's far from representing the excellence of physics in Europe and more generally in the world. And I am assisted with 4 scientific officers. Antonio Bianconi, Chiara Mariotti, who is in this room, Dimitri Batani and Victor Malka, and we are trying, in fact, to make some correction, in fact, to increase the number of excellent physicists in this division. So, for me, and I would say for most of us, the first thing I would like to insist on the motivation for us to do physics is the quest for knowledge. And the quest for knowledge has always been, and in our view, should remain the main driving force for the development of science. And I think the role of Eurasc is to strongly support this cultural dimension in a world which is more and more obsessed by a short-term materialistic return on investment. And this is something important. When I'm listening to the policymakers, even here at the EU, and even yesterday from what we heard, I hear a number of keywords which are societal challenge, economics, return on investment, and I very seldom hear the word culture. And I don't know for you, but at least for me, and I'm sure it's also true for you, the main trigger for our activity is to satisfy the curiosity, our curiosity, which has been the main driver of science for humankind since the very beginning. So I think we should not forget this dimension, and we should fight that in a world which is dominated by a liberal vision, to maintain this aspect of our activity, which is another ingredient besides economic of the well-being of humankind. So I really would like to insist on this point. And just to give a few examples, just a few of major discoveries which have been made in the recent years and which are far away, maybe one day that will come, as that has been said yesterday, but which are far away from a direct, immediate application. But if I look at the impact of this on the public, I think we should continue insisting on this cultural dimension. So here is the discovery of the Higgs boson at CERN in a crystal calorimeter, so in which Chiara and myself have been deeply involved. So you see the decay of the Higgs boson in 2 energetic gamma ray. I don't know if there is a pointer here. Yes? So anyway. So you see the green arrows represent the 2 energetic gamma ray which result from the decay of the Higgs boson. But this is not all. You have seen this very impressive, very first image of a black hole, which has been taken recently. I've not mentioned here, but I would say somehow associated to that. We have seen the first example, the first visualization, I can say, of the gravitational waves resulting from the collapse of 2 black holes recently. We have seen more recently the first image of the James Webb Telescope. All this is far away from the immediate return on our daily life, I would say. If I forget in our daily life the satisfaction of at the cultural level. So please don't forget that, and for the future of our academy, keep insisting on this dimension. Of course, first I would like to mention the very recent Nobel Prize. So this one, perhaps we can see a closer application in our world. So with Alain Aspect, John Francis Clauser, and Anton Zeilinger. And to whom I would like to add, a guy who did not get the Nobel Prize because he died before, but a former colleague from CERN, John Bell. And this guy, in fact, made the experiment with entangled photons, establishing the violation of the Bell inequality, so this inequality which has been produced several years ago by John Bell, and pioneering the quantum information science. And this is a non-intuitive but extremely elegant answer to the famous Einstein-Podolsky-Rosen paradox. So this is also a very, very fundamental input, I would say, to our knowledge. Of course, we should not be strict on that and focus only on this aspect. You have to recognize we should not remain in our ivory tower. And we have to admit that science is also a tool to answer a number of societal challenges. It's certainly the best tool for that. I just give a few examples. In the healthcare, the contribution to the healthcare is, of course, very important in the domain of biology, biophysics, biochemistry, of course, but not at all. This is not all by far. There are many contributions coming from physics, particularly in the domain of medical imaging, of radiotherapy, of material science, for instance, for the development of biocompatible materials for prostheses, in computer science, for the data management, which is a huge problem in the healthcare system today, deep learning, etc., etc. So I just give this example, but I could give many. When Röntgen discovered the X-rays, which in fact allowed him to get the first Nobel Prize in physics in 1901, that was at that time a very, very fundamental discovery, and which was not considered in the frame of this application. But consider today, Röntgen had the intuition, just 2 weeks after his discovery, that it could be useful to look inside the body. And he took, this is the famous picture of his wife's hand with the ring. I don't know where the ring was coming from, but I cannot read. But I think that was fundamental. And this is, in my view, the shortest, the fastest technology transfer example that I know, in fact. But consider that today, 500 million X-ray exams are performed every year just in the healthcare domain, not counting the other application in industry in a different domain. So this is, of course, the societal impact is very important and it should not be forgotten. Another example is the radiotherapy. So you see Marie Curie here, and very, very soon after her work on the radium, some medical doctors try to use a radioactive element to cure skin cancer and then other type of cancers later on. Another example, which is very, very important in the hospital, when you go to hospital, you go to a scan, to a medical scan, whatever it is, X-ray, PET scanner, MRI, etc. The reconstruction is based on the so-called tomographic principle. And the two guys who invented that are a physicist, nuclear physicist, and an electrical engineer. So multidisciplinarity is quite important. A very famous example is MRI. 4 Nobel Prizes for MRI. Not a single one medical doctor. So multidisciplinarity, very important. I give the example of a former colleague at CERN, Dave Townsend, who invented the PET-CT, which is the possibility to record at the same time a functional molecular imaging image of the biological process in your body, superimposed to an anatomical image of your body, but not only that, using a synergy between the two modalities to apply correction, what are called in PET scanner the attenuation correction, which significantly improve the quality of the image. And you see that this discovery, in fact, was immediately boosting the PET market. And now in every hospital has at least one or several PET scanners, and, which are widely used in different domains, particularly in oncology, but also cardiology, brain studies, etc. So, if I take another example than healthcare, energy. Energy is, of course, a very critical domain these days, and science is certainly the best tool to answer the problems of energy production, for instance, with the new generation of nuclear reactor, with possible ways for the transmutation of long-living to short-living nuclear wasted. All the work that you know on nuclear fusion, the photovoltaic, hydrogen, all this is based on scientific work. But also the energy storage, which is a big problem these days, which is basically the missing link in the green energy plans. And here again, science will bring the answer, for sure. Another one is the global warming. Improvement on energy production efficiency, for instance, in the domain of photovoltaic, has to go through scientific discoveries. Improvement on energy consumption efficiency, it's also scientific, will result, in fact, from scientific discoveries. The engineering of smarter electric grid, this is very important, for more efficient energy distribution. You should consider that in energy distribution, nearly half of the energy is lost in the transport, so this is completely ridiculous. And a lot of work can be done in this area. The development of biofuels, the capturing of carbon dioxide from power plants or atmosphere, and turning it into valuable products. So all this is in the domain of science, and science will bring the answer, for sure. So the role of science in society is for me quite clear. However, I see a major concern. It's clear that fundamental science still makes the majority of people dream. Just to give the example of CERN, every year we have requests for more than 100,000 visit requests from all over the world. And so far we can only satisfy 1/3 of them. So there is a demand from the public, which is good. However, I see we all see actually, a small but increasing fraction of the population considering that science, which is often confused with technology, is producing more problems than it solves. This is a concern. An even bigger concern is the fact that an even smaller but also increasing fraction of the population, amplified by the social media, is rejecting science and trying to impose other visions. This is extremely dangerous. The COVID pandemic has been a revealer of this worrying trend. We should resist to that. And this is related to a large part to a deficit of education exploited by people who want to destabilize our society. So there is a concern which is going much beyond the curiosity, the natural curiosity, which is pushing us to do science. But we are part of the society. You should be concerned about that. And we should try to answer this kind of problem. So, for me, one possible way, certainly not the only one possible way to fight against these trends is to reinforce dissemination and education effort. It's clear that educated people are generally less crazy than non-educated people, or they are less, let's say, influenceable than educated people. So we have to be very, very careful about that, and we should reinforce the effort, and I think the academy is certainly a very, very nice tool, I would say, to work in this direction. I just give you the example of what's going on at CERN. As I said, CERN has received many, many requests that it cannot satisfy at this moment. And they have decided to build a huge education center through the help of a foundation and donation. It's a complex which is worth 100 million euros, so it's a big endeavor. And this is now under construction and will be inaugurated next year in 2023. And this system, it's a complex with an exhibition hall for to discover CERN, another one to discover our universe, very interesting complex building for an immersive experience in the quantum world, where you can play uncertainty tennis, you can have a quantum karaoke. Don't ask me how it works, but you will have some nice immersion in the entanglement domain. You can play with virtual particle, quantum tunneling, and things like that. So that is going to be something really funny, I tell you. But we have also very important education labs from 5 to 100 years old people. So education has to start very early. And one very important aspect here is also that what we want in this complex is also to promote the science as such, but to give incentive for young people to go to science, and particularly because physics is physics from this point of view is not the best like mathematics in terms of gender issue, to push female people to go to science. And and also we have a number of exhibition and auditorium things. So just to give an example, but this center is going to be one of the most important education and education center, science education center in Europe and perhaps in the world. And this is, in fact, this kind of thing should be replicated. I really would like to see, for instance, the Max Planck Institute in Germany or other big institute. We can afford to perhaps to spend a bit more on this aspect of their activity, which is extremely important for the future. So, as I say here, the idea is to inspire the next generation and to embark in scientific career, to reach out the general public, to contribute to a positive climate towards science and fundamental research, so basically to fight against the concern that I have mentioned before, but also to influence decision makers, which very often understand very little about science. And I think having them educated could help them to make wiser decisions. No comments. Our ambition for us, so this is my concluding slide, for helping EU to, in fact, is to, we have discussed this many times in the context of Eurasc, is to have this academy playing as a kind of think tank for helping EU to shape the European research area. And in my view, it's going through a number of actions. One is to promote multidisciplinarity. You have seen the example I showed in the healthcare domain. In fact, the healthcare requires combining the effort from different disciplines. This is very important. Within the different physics disciplines, of course, many, but also material science, chemistry, biology, medicine, mathematics, and last but not least, social science. I think we don't have enough connection and common action with social science. I have mentioned on several occasions in my talk here the importance of understanding why the society and the image of science is degrading. And I think our people in social science can help us to understand that and to define perhaps some solution or some action in order to correct for this. I'm very much impressed, and I must say I'm very much worried about the bashing of science in some part of the society. That's something which is extremely dangerous in my view, because it's going against, let's say, the way we would like our society to run in a democratic way. So, be careful. The second point is to foster transnational collaboration to transcend the political divides. The recent example of the war in Ukraine, in fact, has placed us in front of a real challenge. What do we have to do with our Ukrainian colleagues? Relatively easy. We are all tend to help them. But also with our Russian colleagues. Shall we say, we don't want to speak with you anymore? It can be dangerous. When you isolate people who are not thinking like you, they will continue to not think like you. If you keep a minimum of contact through international collaboration, for instance, even if in the beginning they have a different view, at least they will know that some people have another view. And when they will come back in their country, they will put the seed of another vision, which the media are not distributing in their country. So this is something that we should be concerned with. So for me, international collaboration, international contact is also a key to re-establish some kind of equilibrium in the vision of the modern world. We have also to propose translational measures to reinforce the societal impact. Now, it's very seldom that a single discipline can make a major impact on the society. Very often, we need the combination. We have heard mathematics, for instance. Mathematics has been considered for years as a kind of isolated. But you find mathematics everywhere, everywhere. And without mathematics, you cannot do anything. So this is just an extreme example, but what is true for mathematics is true for all our disciplines, and I insist also for the social sciences. And, okay, so this is, I said already. Of course, these translational measures are important at the societal level, also to support technology transfer action in the domain of, in the main societal challenge, for the main societal challenge that you have to face in the coming years. So I will stop here. I hope I did not give too many directions or too many, but I think this is my vision for Eurasc and some domain that on which we should be concerned with, and where I think, because I want to be positive, we can have a positive action. Thank you.
Open our window of our expertise multilaterally. So, who wants to put?
Thank you, Paul. That was very inspiring. I just wanted to back up the idea about communications with the Russian scientists. I was in the mid-1980s part of a group which worked with Russian Soviet scientists on nuclear winter. This was the idea about if we exploded a lot of nuclear bombs, then this would block out sunlight and things. And that was a collaboration really between Americans, the UK, and Soviet scientists. And I do think that it would be in our interests and also a positive move if we were able to to talk to the Russian Academy of Sciences, because I'm sure they are as horrified as we are about what's happening in Russia at the moment. And I do think putting a connection out to them would be a positive move.
I think this is, well, the situation with Russia is rather complicated. In fact, we had a long debate at CERN because, you know, we're in international collaboration, and the CERN Council, in fact, has been discussing at length the problems, in fact, this problem. It's clear that we have to make a distinction between individual and the institutional level, let's say, of the organization of science, which is actually under the control for many institutions of the power. Just to give an example, maybe, well, we should not be shy. I can give names. Mr. Kovalchuk, who is in charge of the Kurchatov Institute, of the Dubna, Prodvino research centers, is the son-in-law of Putin. And so that makes, at the institutional level, the connection relatively difficult. However, at the personal level, I can tell you that in domain that I know, in fact, in the domain of physics that I know, all my colleagues are extremely sad about this situation. I just can't give you a report about a mail I received from a very, very famous colleague at the Lomonosov Institute who dared to write in an email, "I'm so sad about this situation. I don't know what will be my future because I am not allowed to collaborate with the external world." And this is this kind of, I don't have a solution. Very honestly, I don't have a solution. But we should not forget about these people. Because this is these people, as I say, which could be the vector of, let's say, new ideas or new vision or simply new information, because you know what is the information at this moment in Russia, in the country. So we should not forget about that. There is, of course, the high-level diplomatic level, but there is some kind of diplomacy under the table, which has always been important in humankind, let's say, the organization of our society, and particularly in the difficult moments. So again, I don't have a solution, but I think we should share the concern.
So,
about the dissemination, there is a good opportunity that it could be used. That is the 11th of February is the International Day of Women and Girls in Science. And in the region around CERN, we go into schools from elementary school to high school, lycée, what do you say, high school? And we present what we do. So I'm a researcher, what is my job? It's not only physics, but also biology, many kind of science. And this is very effective to communicate with the kids and tell them the beauty of the work and the importance of the curiosity and of the passion that you have in your work. And I think this is it's a very extremely good way to really communicate with the youngest generation.
To go along your comment, Chiara, I would like to mention, and again, because what we need to give is some guidelines, let's say, or some wishes about the role, some actions of our academy. One thing that I notice is that we have a fantastic situation in Europe, in fact, that I just come back from the United States. Our colleagues in the United States really are somehow jealous of this system, which is the way the European Commission is supporting science. This is very good. Can be improved, but this is something which is unique, rather unique. On the other hand, in all the programs of the European Commission, I don't see too many which are going in the direction to support this dissemination and education. And I think perhaps this is something that we should convey to the European Commission to reinforce this activity. There have been a lot of effort, again, with a liberal view, which is important, of course. The EIC, for instance, is a very fantastic new program to ease the technology transfer to industry and to improve the economic weight of Europe in the world. Fine. But in terms of transferring, in fact, the best of science to the public and to the children, to create incentive for more people to embark in these difficult but fascinating careers, I think maybe the European Commission should do more. Just one aspect, and it's a complex system. I just finished my sentence. It's a complex system. Just an aspect, for instance, the direct action on the children, for instance, is one thing. But another thing that actually CERN is doing, and I think is very good, and I'm personally involved in that, is to transfer first to the teachers in secondary schools. So next month, actually, I'm going to give a lecture to teachers in schools so that they can transfer themselves with their knowledge that we don't necessarily have, education knowledge, education skill, to the small children. So this is something which is important to consider, to organize, in fact, a more efficient education system.
I terribly enjoyed your plea for a curiosity-driven research, for dissemination, for the role of science in serving mankind. But what is new? That was true last year, it will be true next year, and more dangerous in my point of view is the fact that we are a minor part as our academy in worldwide academies, scientific societies. We disappear in this argument. My question, where specifically would be the role of our academy? Every scientist would basically claim that and can claim that, but my point is we would need projects to foster, say, interdisciplinarity and make the difference from another society. I think this is an urge. We can now go on and say, talk about the importance of chemistry and biology and serving mankind, all true. But we need something where we make the difference in a project.
Okay,
that we have more interdisciplinarity than others. Okay, that would be my...
You're right, in fact. But in fact, bon, first of all, let me say that it is with small drops that we make big rivers. So this is our contribution, as small as it can be, will be useful. The second one is that there is a big difference between our academy and all the academy, and actually this is for me the motivation to have joined this academy. It's because it's not national, it's European. It's transnational. And for me, that can make a big difference. Of course, it's up to us to do it. And I think, I would say, I would redirect your question to our president, because this is something that should be a major concern for him. And I'm sure it is.
Hello? So
yes,
it's the last
back
question.
to the relation we have with our Russian colleagues. I think that Eurasc sent a good announcement at the beginning of the war, not with the raw terms, and I think it was what we had to do. And from a personal point of view, I had many connections with this Russian colleague because I organized several symposia in Russia, in Siberia, or even in Far East. And I sent them, this was two months ago, a letter saying, okay, we had together good relation, friendship, and we'll have the same meaning with you. I will not change. And please do not, it is not necessary for you to reply to me because I was afraid. And most of them replied me, and 3 of them asked me, we would like to cooperate again with you. So I don't know exactly what I could do for them, but these these guys were excellent scientists. They are totally separated from our world, but I think we should do something for them. This is.
Okay. I think it's time to move, but just to answer to Professor Mullen, the idea is the last thing that we have to lose. I have just to tell you, and I'm very proud, it was a Portuguese called Zé Gago, that we have ERC thanks to him. He has had the idea that we should unite all the people, and nobody, as you said, say, you never will get success, and we got success. When we speak about the dissemination, he also was a clever guy with a challenge. What he is saying, science alive. Zé Gago created this 20 years ago. Now is an example for Europe, and in the Parliament today, it will be a commemoration about this type of idea. So the worst thing that we can do is to give up. Never give up. And we count on all of you to go further. So don't say things are not, there's no way to go, or they are so incremental that does not make the difference. No, different. We heard yesterday about the picojoules, that when you try to increase this picojoules, you create a problem for the Earth. Picos can be great if united.
Good morning, everyone. I see that every division chair has understood differently the challenging presentation they had to do today. But that is biodiversity. It's really great. And I fully endorse what Paul has just said. And you will see some overlaps with some of the items I want to mention. The purpose here, for me, is not to talk to the chemists in the audience, so you can lay back and relax. I'm going to talk to the non-chemists. What I would like to show you and discuss with you is the diversity of chemistry, and the roadmap for our division is just to be present on all fronts, as simple as that. If you look at chemistry, we don't have a pointer, I'm afraid, so unless someone has a magic pointer that works on this sort of screens, I don't. Chemistry, of course, the definition, the study of matter, its transformations, and the energy changes that accompany those transformations. This is a science, but also an industry, and I'll come back to that later. This is a very important point on which perhaps our academy could be more present. This is something to be discussed. Fundamental science, curiosity-driven, nurtures innovation and application. And you have here a diagram where the XY coordinates tell you the developments. Technology in the X-axis, impact on the market on the Y-axis. And the best, of course, is to be disruptive with technology or new business model that disrupt existing markets. But that's something which is often not predictable. But that's why we have to be present on all fronts. Of course, in Brussels, I cannot miss the connection or the mentioning Solvay. And you see in the corridor some pictures taken in the famous Solvay conferences, which gathered the top scientists at the time. Soda ash was used since ancient times for producing glass, textiles, soap, paper. And it was a very traditional industry. In 1861, Solvay, Belgian chemist, patented an improved method to manufacture sodium carbonate. And this became a very wealthy and very fast developing industry. Now industry in chemistry looks differently, a much bigger scale at the BASF plant in Ludwigshafen. Now there are about 1.2 million workers in chemistry, about 500 billion turnover, about 10 million research investment. And the European chemical industry, the wealth generating sector, something not to be forgotten, including by politicians, of the economy, and a major contributor to building a sustainable future for Europe. And the European Commission actually has recognized that the chemical industry is its indispensable role to help society achieve the new European Green Deal objectives. I'll come back to that in a minute. Green chemistry is perhaps a word you've heard sometimes. I'm not talking to the chemist again, apologize. It's also called sustainable chemistry. This is an area of chemistry and chemical engineering which is focused on the design of products and processes that minimize the use and generation of hazardous substances. And there have been a lot of top publications in this field, which are given here in the references. IUPAC, which is International Union of Pure and Applied Chemistry, is another definition which is very similar. Design of chemical products and processes that reduce or eliminate the use or generation of substances hazardous to humans, animals, plants, and the environment. Environmental chemistry focuses mostly on the impact of polluting chemicals on nature, whereas green chemistry aims at preventing pollution and reducing consumption of renewable resources. So there are complementary approaches, but green chemistry has generated a lot of attention in the last 15 to 20 years for obvious reasons. The overarching goals of green chemistry, which is basically more resource efficient and inherently safer design of molecules, materials, products, and processes, can be pursued in a wide range of contexts. And everyone now is aware of this, including industrial partners. They all have that on their roadmap. 12 principles they've been identified as consisting in the core of green chemistry, which are listed here. And the American Chemical Society has produced a little pocket guide, shown on the right-hand side, which summarizes these 12 principles, and that is widely distributed to students, even to schools, etc. Prevention, atom economy, less hazardous chemical synthesis, safer chemicals, etc., etc. I will not go through all of these, except for one. Catalysis is explicitly mentioned here. And that is a very important word, not only in fundamental science, but in applied science. But what is catalysis? If you look at the chemical reaction, starting on the left, you have two compounds, A plus B, that you want to react chemically to give product C plus D. You don't go through a straight line to go from the precursors to the product. You go up to mountains and hills. The mountains mean energy consumption. And the valley, you gain again some energy. So this is the reaction profile, as we call it. Catalysis on the bottom left reduces the height of the mountain. So it facilitates the transformation. It will act on the kinetics of the reaction, not on the thermodynamics. You cannot change thermodynamics, but you can change the kinetics. It's like if you go out on a bicycle, if you're facing a mountain, you try to go through the pass and not to the top of the hill, unless you're a masochist. You're really training for the Tour de France. Otherwise, you try to find the easiest way between the peaks of the mountain. That's exactly what catalysis is all about. Catalysis includes all aspects of heterogeneous catalysis, which means the products and the catalyst are not miscible, homogeneous, supported, biological, through enzyme catalysis. About 85 or 90% of all chemical processes now involve catalysis at one step or another in the production, dominated by heterogeneous catalysis for technical reasons. Homogeneous catalysis, and I've listed here some key reactions we find in industry: hydroformylation, carbonylation, oxidation, hydrogenation, name it, have all been developed at the industrial level because of a better understanding of the basic chemistry associated with them. And many of these fundamental efforts were just curiosity-driven, with sometimes no idea about applications that emerged 15 or 20 years later. This has led to improved activity, chemo-regio-stereo-selectivity, which is a big issue. You want to be targeting the product in the best possible way. And if you take a reaction like this oxo-catalysis, in the past 15 years, it has improved by a factor of 10,000 by having better technologies, by replacing a catalyst based on cobalt with rhodium, although rhodium is more expensive. It has led to major improvement in the catalysis, trying to work with the ligands, what we call the coordination sphere of the metals, etc. So major improvements been made. Now recently, You may have seen that the Nobel Prize in Chemistry was awarded to these three scientists for the development of a reaction called click chemistry, which is metal catalyzed, and which allows reactions to be performed in biological media without perturbing them. This is why it's called bio-orthogonal. You can perform two without interferences. The catalysis has been rewarded the previous year, also by the Nobel Prize, with these two gentlemen for the development of asymmetric organocatalysis. Asymmetric brings about the idea that key molecules are often chiral, like left hand and right hand. They cannot be superimposed. That's chirality. Well, in 2010, again, catalysis, palladium catalyzed cross-coupling reaction, how to couple carbon-carbon bonds with the help of palladium as a transition metal. That again was a key reaction used worldwide by thousands of chemists on a daily basis. Echtel in Germany in 2007 got the Nobel Prize alone, which is quite remarkable, for his studies of chemical processes on solid surfaces. And the quotation is, Echtel was able to map out details of a process of great importance in the production of artificial fertilizer, the Haber-Bosch process, in which nitrogen in the air is converted to ammonia via an iron catalyst. Without ammonia, no fertilizer, no way to feed the planet. We need chemistry to feed the planet, despite what some people think. Now, this Haber-Bosch process is a very interesting one. Enzymes in nature, nitrogenase, are able to convert the nitrogen we breathe into ammonia under very mild conditions, ambient temperature. Chemists have not achieved that yet. The only process we have is a so-called Haber-Bosch process, which produces ammonia based on an iron or ruthenium catalyst, high pressures, high temperature. So we still have solutions to find to improve these processes. But this is a huge advancement in science. Now, the Haber-Bosch process, mind you, because of the conditions, requires something like 3% of the world energy. But we have no alternative, otherwise no fertilizer. And this is the structure of the active site of the cofactor of the enzyme, beautiful cubane type structures, as we call them in chemistry. If we go back to 2005, again, catalysis was rewarded with the development of metathesis reaction, which is illustrated in the bottom, where basically you have an exchange of double bonds between olefinic systems, which have a huge application in organic synthesis, pharmaceuticals, name it. Again, very fundamental chemistry. When Yves Chauvin on the left-hand side, which was working in the French Institute of Petroleum, I happened to know him quite well and collaborated with him for many years, understood the mechanism of the reaction. He said, what's the point, this is, first of all, a lot of people argued, this is crazy, stay home and do nothing. And when he got the Nobel Prize about 30 years later, he was interviewed on television saying, oh, I'm now retired, it doesn't help me anymore. It's so long ago, I almost forgot about it. So it takes time to mature. So always keep patience. So in 2001, asymmetric catalysis was rewarded, again, left and right, something which is instrumental in pharmaceuticals. It can be a very positive drug or a poison if you get the wrong hand, so to speak, with these three gentlemen who made fantastic discoveries on how to catalyze reactions for hydrogenation chemistry. Chirality, that was a slide borrowed from one of the members because I consulted membership to prepare this little presentation, and I'm very pleased that many of them sent me material for this presentation. I'm very grateful to them. Chirality is everywhere, in novel materials, in polymers, in drug discovery, in materials, in leads, perovskites, etc. I can't go through all the details, it's just impossible, no time for that. But chemistry, I would like to emphasize, has numerous interactions and interfaces with other disciplines, as mentioned in previous talks. Chemical engineering, biology, medicine, pharmacology, agricultural sciences, material sciences, physics, numerical simulations. And that makes chemistry a particularly enabling science to address key challenges. And there is a recognized need to create pathways for the chemical industry, for the production in general, to be truly sustainable, circular, economically viable, and will meet consumer needs and acceptance. And this is a very important aspect, particularly in view of what Paul was emphasizing. The media have basically no scientific knowledge in general. And for them, anything is bad news if it's new technology, or chemistry in particular has a bad image, because they just don't understand that they wouldn't be there without chemistry. The transformation from a petroleum-based era to alternatives is one of the key issues. It requires, of course, interdisciplinary approaches to develop new concepts and application, and that is curiosity-driven. Perhaps something will develop, perhaps not. That's not the main objective initially. I mean, that range from physics to material science for the study of reaction on surfaces. We've seen reaction on surfaces, Echtel getting the Nobel Prize in chemistry for that, to biochemical processes and enzymatic chemistry. New materials for quantum computing and energy-efficient computing architectures. The development of advanced operando tools to monitor reactions in situ with modern technology, modern instrumentation. Spectroscopic techniques at a wide range of length and time scales. The use of artificial intelligence for data mining. There are millions of chemical compounds around, so we need to better search mechanisms for properties to make computer-based predictions. We have a wealth of compounds. We don't know how to address them properly in terms of identifying the key properties that we need at a given time. To deal with an emerging paradigm, chemical systems should be designed ab initio with the main drive of being sustainable, recyclable. Often this will translate into accepting a fair or good figures of merit rather than aiming at the best yields or best performances. This has to be conceived a priori. You know, a lot of people are in favor of wind energy. It's great. But what do you do with the blades? Nothing. It cannot be recycled. They are buried in the ground in the US. Are the green in favor of that? No. That you cannot recycle the blades? This is a limitation in the exercise. You know, science is a comprehensive business. You cannot just isolate the fragment. To promote citizen science, efficient interaction with schools, it has been mentioned earlier on. We have great overlaps between various divisions. This is fantastic. To make science attractive to the younger generation. Energy has been mentioned as one of the challenges. Efficient buildings with less leaks. New materials for better isolation. Better use of methane through catalysis. Methane is burned in oil fields. Can we do something better than just burning methane? Wasting carbon, producing carbon dioxide? Yet, but methane is a difficult molecule to activate, to do chemistry with it. There are ways. It's not optimized yet, but this is a big challenge. Reduce carbon dioxide emissions, capture and transformation of CO2 into useful chemicals. Catalytic cracking, of course, is a process that you're aware of. With the oil crisis, you know that cracking is essential to produce gasoline and light molecules. Nuclear energy, new reactors, how do we handle the waste materials? The metallurgy that goes with it is high tech. Now we know that some companies have lost the expertise of how to make the big reactors you need. This is sophisticated metallurgy. It is not the steel industry from the 19th century. It is something highly sophisticated, requires science. Water at the source of hydrogen and oxygen, to use water in an efficient way. Fuel cells, solar cells. This is a big challenge. Photocatalysis, using light as an energy source for catalysis, electrocatalysis as well. But how do we store this energy if we produce it? We need batteries. Are we autonomous in Europe for batteries? There is a big effort, but some other countries are much ahead of us. This is a flow sheet that comes from a science paper in 2018, which I don't have the time to discuss in detail, that shows an integrated system map that can provide essential energy services without adding CO2 to the atmosphere. You've seen green, electricity generation and transmission, in blue, hydrogen production and transport. Hydrogen is not an energy source, in contrast to what most journalists say. This is a vector. You have to produce hydrogen. You cannot go down in the mines and get hydrogen. This is not an energy source, this is a vector. You have to produce it, and you produce it through electricity. Where does the electricity come from? Etc. So you have these channels here illustrating various possibilities without adding CO2 to the atmosphere. Batteries. This has been rewarded again by a Nobel Prize in 2019 in chemistry for the development of lithium-ion batteries with these three famous gentlemen. Medicine, pharma, new antiviral drugs, drug transport methodologies to carry active species into the body at a given place. You need to put them in a cargo. These are often chemical compounds with very well-designed structures. Improve targeting of a specific cell or organ, nanoparticle-based vaccines, and you've heard that with the COVID. Without the chemistry to surround the ARN, it wouldn't have been possible to deliver them. Now there are over 26 nanoparticle vaccine candidates in advanced clinical testing and more than 60 in preclinical development. It's given a huge boost to this area. Focus on drug molecules, if possible, as simple as possible. Photoactivable, chemically activatable prodrugs, precursors of the drugs. In cosmetics, perfumes, chemistry is everywhere. Big companies in Switzerland, Firmenich produces perfumes, introduced catalysis about 30 years ago for a major change in the whole production of these perfumes. Food additives, just one example, you all know vanillin, you love ice cream, I'm sure. This is the #1 natural aroma that people love. The natural aroma, the natural vanilla, costs about $50,000 per kilo. The synthetic one, which is the same molecule, but made in the chemical industry, cost $15 per kilogram. And the molecules are, of course, identical. Of course, what you can anticipate is a massive fraud on this market, because the market is about 15,000 tons per year, and natural vanilla can only deliver 40 tons. But it's the same molecule. Well, there is an interesting biosynthetic vanillin approach by Rhodia in 2000 by fermentation of ferulic acid, which is in the envelope of rice grain, which has a much lower cost, $700 instead of 50,000, but still more than the $15 in the chemistry. But this is more biosynthetic, so I think it's more acceptable for the general public, even if they don't understand the structure of the molecules. It's just here for the chemist. If you think of chlorophyll, and we all love green plants, if you go to the supermarket and want to buy deep frozen peas, they'll better look green, otherwise you will not buy them. Otherwise they will look sort of grayish, and you say, well, that's not good news. So how do they make it to let the peas look green? Well, they just replaced magnesium with copper in this very molecule, and then the peas are green. So maybe you should think of eating gray peas, which may be healthier than having some copper to go with the green color. It's up to you, but you better know. We mentioned enzymes. This is again in 2018 Nobel Prize for these three scientists. And I mentioned enzyme yesterday in the Laudatio for Manfred Reetz with the directed evolution using enzymes. Agriculture, forestry, fertilizers, we mentioned, we talked about ammonia already, insecticides, pesticides, fungicides. Look at forests. The damages, some bugs we can't really take care of properly, and et cetera, et cetera. Materials has been mentioned before. Physical properties, electric, magnetic, photophysical, hardware and devices for microelectronics. That's where chemistry also plays a key role. Smart textiles, even in daily stuff like sport shoes, skis, the advancements made, and you see the records in the Olympic Games every time because of new materials. They don't come from the sky. Someone has conceived them and made them. Special lubricants for high-performance cars, engines, or flights. Even in arts, you find physical chemistry and cultural heritage, a fascinating area where you can identify, and it is regularly coming into the media, when the Leonardo da Vinci painting has been reactivated or re-identified, or a Rembrandt has been analyzed as coming either from Rembrandt or the school of Rembrandt. Physical chemistry can tell you a lot of information about the dating, the renovation, the use of pigments, etc., etc. Europe is the second largest chemical producers in the world. Here are the numbers. No comment needed. But a comment on the next slide. the EU 27 market share has dropped significantly in the last 10 years. On the bottom left, you see US. EU 27 has dropped from 19.3 to 14.3. US has dropped as well. India, more or less stable. One has developed massively, is China. I think Europe has to think about it carefully. Because it also contributes to 12% of the manufacturing employment. These are the top 10 sectors in terms of employees. The chemistry ranks second here in blue. So we have a huge market here for the next generation of scientists. Do we want them to be in an environment where we will get no job because there is no chemical industry anymore? Here is a curve which shows the greenhouse gas emissions in red and the chemical production in green. And you see that with time, the production of green gas has decreased, while at the same time, the chemical production has increased. So these are decoupled. So clearly, chemistry is part of the solution, no longer part of the problem. This is a very important aspect to consider. I mentioned earlier on that I had been very pleased to see the feedback from many members of our division, and I have listed them here. They provide me with my ideas or slides or documents that I could use here, and I'm very, very grateful to them for their reactivity and their involvement in the life of our division. You may remember that in 2019, UNESCO declared the International Year of the Periodic Table, and I'm sure all of you in school or in university at one stage or another have learned about what the periodic table is all about. You may have forgotten the column and the rows by heart. This is a manuscript of Mendeleev, published in 1869. But I'm sure that on a daily basis, you use the periodic table, sometimes perhaps even without knowing it. You always start your day with coffee. And you usually finish it with wine. And I'm pretty sure that our president has brought some bottle of Porto with him today to celebrate the end of this symposium. So I would like to thank you very much indeed for your attention. And the roadmap for us is very simple. Be present on all fronts. Thank you very much.
Waiting, so we can know 2 questions, please.
Thanks a lot. I'm not a chemist, but I have the following question. Currently, we see an enormous increase of the energy prices, and I think this definitely affects the chemical industry, particularly in Europe. How do you see, will it result in a continuing of the trend that you have shown, that in Europe the percentage of chemical industry will go down and in other parts of the world, particularly in Asia, will grow up? Or with other words, what can we do in Europe in this particular situation?
Yeah, this is a central question. I mean, I would make predictions. You know the saying, I think it's a Chinese saying, predictions are very dangerous, particularly concerning the future. Now, energy is definitely a central issue. It's not clear to me why some prices have exploded recently. Not everything came from the hot areas at the moment in Europe. Some did, but not everything. The coupling mechanism between production and prices is something rather mysterious to me. How can it be explained that some of the prices got multiplied by 800 suddenly? So some companies, major companies, small companies are in very tough difficulties. Some of them might just have to close. Even in my town, a couple of bakers said, you know, I cannot continue. I'm not going to sell the French baguette €2.50 instead of €1.20. My customers will kill me. So I cannot continue. The price of energy is just too high. I will close the shop. So that's real life. So I think we better find solutions. Of course, there are political components which I cannot talk about. I'm not an expert. I have my opinion, but that's another issue. We should be based on fact. Science policy actually should be a science. And that's often what politicians forget. Science policy should be a science. So if the energy prices continues to grow or remains as high as now, I think we will have major problems in our industry. Not only the chemical industry, but it is a provider of so many things we need in other areas of the economy, of health, of whatever, name it. I've tried to illustrate part of the landscape, that it will have major consequences that we cannot foresee at the moment. We can just hope that we can find better solutions. But at the same time, this provides an opportunity to emphasize the research on particularly catalysis. How can we make better use of natural resources? Methane, for example, is quite abundant. We don't know what to do with it, or barely. So there is room for improvements in our way to handle the natural resources we have. Better yields, better selectivity in transformation, so waste, diminishing the amount of waste, targeting better productivity so that the price per kilo, per whatever ton, it gets reduced. But this is a very, very important issue. I think Europe is aware of that. They will have special programs to help some companies, but is that sustainable? I don't know how to answer that.
So this is our challenge for the future. I think I cannot. Oh, okay.
I would like your opinion on how chemistry can help recycling, especially in terms of plastic, because there are some real barriers now.
Yes, yeah. Now that's an important one. Many companies are working now on the recycling of plastics and polymers, and very successfully, actually, very successfully. Not everything can be done. I mentioned the blades of wind turbines, that we don't know how to do that. So the problem often is when you conceive the material, to integrate the capability of recycling it at the end of the life cycle. And this has not been always done. They produce the material and didn't think about what to do after death of this material. So instead of just burying him in the ground, you would have better ways to do that. So in the area of polymers and plastics in general, there are small companies, startup companies, which have been very successful at developing new methods to deal with that, and bigger companies as well. This is a huge market, how to deal with this waste. And this is an energy source. But of course, you have to find a way to handle these in the most economical way possible. Polymers is a huge market. Without polymers, we wouldn't be here. Everything we wear, we do, has to do with materials, polymeric material. Fantastic advances in the last few decades. You know, this is an amazing development. It's a major industrial component as well in industry. So this is something we really have to protect in a way, in a clever way.
So thank you very much. Let's thanks to the, I'm sorry, but we are half an hour. Now it's time to hear Alberto from Engineering Division.
So, good morning to everybody. I think that the main objective or purpose of an academy like ours should be to defend science and maybe defend the correct development of science. I will explain better with some slides and pointing some more details. According to also to the yesterday roundtable in debate. So just a short notes, but I will say something also of very general, I think, the first part of my speech. Then the second part, I will give you some examples, some more personal examples, just to explain better what I intend. So, science today has four very challenging competitors, I think. First of all, technology, then we have economics, and lastly, politics. Therefore, we have in some way four different spheres of influence. I include also science, of course. And we have, of course, we have interactions between them, but I think we should avoid overlapping in some way. Overlapping. I would try to explain a little better. For example, when we speak about technology, it's very well known that science needs technology because we have to conduct our experiments and also computation. So it's very, very well known in this sense. But also technology is a final goal or output result of science. So there is a very strict interactions. Nowadays there is also some confusion sometimes about these concepts and the contexts, different contexts. So the danger, what can happen is that we have a science which is not considered so important. In some way, the role of science could be underestimated. This is in some way, we can also say, like my expression, could be squeezed between the two technological contexts. The first is the instrumental one, the second, the industrial one. So this is a very important point, I think, everybody can. We have economy. Economy, I think that a strong economy or rich economy can help science very much, of course, because you may think that frontier research, what we call also cutting-edge research, needs a lot of money. At the same time, the results of this research, very advanced research, can help economy. So there is a loop, also a strict interaction between these concepts today. No? In the historical times, this relationship were much less strong, of course. No? Also, in this case, if the loop is not good, is not virtuous, we have problems. And so, in this case, economy cannot help science in the right way, of course. Politics, yes, also in this case, we have strict connections, of course. Politics are twofold task. The first is that to select regarding basic science, has to select the topics to be financially supported. Then, at the same time, politics has to select also what we call applied research, no? or innovation, and so on. So, also in this case, we have to reach an equilibrium. In some way, if especially basic research is not always well financed today, you know that. And I think that this is a major point, because if basic research is not well supported, or rightly supported, we have problems for all the system, I think. All the system is very badly influenced. Then we have another context, which is different from the other ones, but for an academy is also very important, I think, philosophy, because I understand this very general, but in this academy we have also humanities, so I think also a debate about these things would be very, very interesting. Philosophy is my interest from many times. Since when I was young, I was very interested in philosophy. Very often we don't see this strong relationship between science and philosophy, but really the current philosophical main streams can influence in some way strongly some important theories. At the same time, this theory on their turn can influence the next future philosophical trends. So it's very, very interesting, should be interesting to deepen also this kind of aspects in my opinion. Then we can say that today, the mainstream, or we can say most successful epistemological theory is the critical rationalism by Karl Popper, where there is this important theory that we have the change or shift, which is a weaker word, change or shift of paradigm, which means that the theory could be always falsified. Falsified, this is a technical word in some way. Falsified means that in some way it could be contradicted and by some aspects, or cannot explain new phenomena. So it's a very important point, I think. And today, the specialists, of course, of these disciplines are oriented in this way, I think. But from the most practical point of view, we see that some colleagues are rather, maybe they are not so conscious about the philosophical implications, but they are, in my opinion, quite conservative and dogmatic. So sometimes, no? They defend very, very strongly some theories, and it is, I think, more and more difficult to put into discussion discipline theories and to change them even a little. This is I think, is a strong trend, very strong trend. It should be interesting to discuss in an academy about that. So the main concept is that of change or shift of paradigm, no? Which is, in other words, what is exactly? It is we can say that a theory could be substituted by another one, which is usually should be more advanced, and including also the preceding one. Not always to contradict, of course, but to include. Okay, just I forgotten to say that this the conservative attitude of some scientists is to see it in a noble way. I think is very adherent to the neo-idealist stream, which is, for example, contingentism, conventionalism, and so on. So also that could be explained in some way, of course. So it's a problem of conflict between, of interest, I think, also in some way, but conflict between ideas, no? Is also very important. Is the mechanism of science in some way. Okay, I want to say that in my activities, I had the fortune, or maybe misfortune, to meet with three different change of paradigms. No, I should say something about that. Just an example, of course, nothing else. The first was the use of catastrophe theory to explain the brittle behavior of very large structures, which is a phenomenon which cannot be explained in a rational. It was not explained in a rational way, in my opinion. So I introduced this concept with computations, of course, that we have a transition from ductile to brittle to catastrophic, which means in the load versus deflection, it means a force as a function of displacement, for example, or a deformation, you have this, you see the third curve, the bottom curve, is not monodrome, no, in mathematics, and it means that we have not the possibility to control the phenomenon. So you have a drop of this. In some way, if you control the displacement, you have a drop. You skip the catastrophic branch. No, it's very technical, but mathematicians can, I think, understand very well. Anyway, it was a very rational way. I was very heavily personally involved in this discussion. It lasted many years, in Europe, but also in the world, I think. In some way, today may be the frontier of strength of material, no? You see that the hatched area, or the shadowed area, represents the emitted energy. So it's very important also from to measure the energy which is emitted by vibrations or even kinematics, kinematic energy by the structure of the specimens and so on. So a very long debate, and in fact, I'm speaking about the change of paradigm, or maybe possible change of paradigm. We don't know at the moment, really. Then another very interesting, especially for mathematics again, point of view. In this case, there was, as a discussion, we can say the use of renormalization group theory, which is a very typical method of physics, or fractal geometry, which is very typical for mathematics, to explain what? In this case, the scale effects, so the change with the scale, of the mechanical properties of materials. So a very important problem for specialists, of course. And we see that I and other colleagues propose this fractal geometry, just as an example. This is an invasive domain in the sense that this von Koch curve, which is just an example, has a dimension which is between 1 and 2. So it's invasive in this sense. The dimension is 1.626, so it's very abstract for not mathematician. Of course, we use this concept for fracture surfaces. You see that the extreme on the right is the so-called Brownian surface with dimension 2.5. No, it's very abstract, but it can explain very well and very realistically also scale effects in materials. A lot of fighting about that. A lot of fighting. Then we have lacunar fractals. This is archetypes, is a Cantor set, or Cantor dust, which is a dimension, which has a dimension between 0 and 1. This iteration you see, and exactly as a 0.631. And you see that this concept, we have extended this concept to 2 dimensions, the Sierpinski gasket, carpet, which is very famous in the field of fractals. And you see that there is also iterative series of sets, and you have a set with an area which is 0. Incredible, but it can be proved that it is 0. Exactly, it's between 2, the dimension, so the area is 0, but the dimension is between 2 and 3. Excuse me, it's between 1 and 2 again. 1 and 2. And this is very useful to describe the sections of damaged material at the peak load. When the peak load is reached, we have a situation like this with cracks and the voids, etc. Also, in this case, we can explain everything. What is I don't know time, of course, to explain which are the conclusion about that. But it's very interesting to see that it was very realistic, very close to the reality, but was rejected, especially initially by the community, scientific community, which was very, for me, was surprising. I can confess that it was surprising. Not now, of course, but in an academy, I think it should be interesting to discuss about this, these things. So last example is the use of LENR is low energy nuclear reactions to explain the chemical evolution of our planet, in particular of the crust, of the Earth crust. Just the last graph is a complicated graph where fundamentally you have the abundances of the elements of the Earth in the last 4.5 billion years, of course. They change a lot, We have this data since a few years because they have between 20 and 30 years old, this data. It's very interesting because we see objectively, I think, are not my data, of course, that ferrous elements are decreasing by 12%. At the same time, silicon, aluminum, and oxygen, and carbon increased by 12%. So we have a perfect balance. You can check, even it's a double check, because we had two very severe phenomena. The first was the formation of tectonic plaques. The second is the most severe tectonic activity. And you see that we have a perfect balance. What is incredible is that also for the cycle of calcium, we have the same. We have a perfect balance, not 12, but 8.7. So I want to say that alkaline terrose or alkaline earth elements, which are calcium and magnesium, disappear, exactly 8.7. At the same time, we have alkaline, sodium and potassium, but also oxygen with the great oxidation event that biologists know very well. No? It's a sudden increase in oxygen. So what is incredible, at least for me, is that there is a perfect balance, 8.7 disappearing and 8.7 appearing. So I want to say that I and other colleagues, but I was the first, I think, our position was that cannot be a pure chance. I want to say that the migration theories that affirm that this is also a problem of displacement of matter cannot be true because migration cannot imply perfect balances. Perfect balances can be implied only by transformation of the matter. This is a very important point, I think, but scientific environment was in some way surprised, but no reaction. I think that in an academy like this is very free, I think, could be discussed some change of paradigm or possible change of paradigm like that. Thank you very much for your attention.